Good morning. Good morning. A pleasure to be here at Heswall to talk to the U3A here. So yes, the weird world of the very, very small. I'll be looking to start with just to get a sense of scale, to remind us how small is small, and then contemplating the idea that a sense of symmetry tells us a little bit about what the world is made of, because ultimately the world is made of very small building blocks. And we'll finish by looking into the quantum world itself. So, just to get a sense of scale, we're familiar with things that we can see down to the sort of millimeter scale. So here's a little friendly malaria parasite bearing mosquito. And we can see that details on our skin, we can see down to sub-millimeter with our eyes, but we can indeed make things even smaller than that. This is a natural structure. Do you recognize that? Not a coronavirus. Coronavirus would be smaller still. So this is a pollen grain. So here we're talking about fractions of a millimeter. So now we're talking about a scale that we can't see. So we might be able to see mosquitoes, we can see things down to a fraction of a millimeter, but when we get down to, let's say, 1/10 of a millimeter or 1/20th of a millimeter, or 50 microns, 1 micron being 1/1000th of a millimeter, now we're getting to the point where our eyes give up on us, and hence we have to resort to microscopes. But although that's the natural world, we can build things on similar scales. Even though we can't see on a scale that's sub-millimeter, we can build things on a scale of sub-millimeter. This is a set of gear, ratchets, etc., on a scale of hundreds of microns or so. So this entire mechanism would be almost too small to see. But again, we can build mechanical devices on that scale, though you could ask, why would you want to? But of course, in terms of miniaturization, it's been driven by the electronic revolution. And these days, we can put enormous numbers of electronic components onto a silicon chip. So these days, in a space of on the space of a square millimeter or so, we can place hundreds of millions of transistors. And that's on something that's only a few square millimeters. Chips themselves might be square centimeters in size, so we can get billions of transistors onto a chip these days. So the size of individual components on a computer microchip would be of order nanometers. I've said here of order 10 nanometers. It's now possible to make devices on chips that are smaller than 10 nanometers. They are literally getting down to a few nanometers in size. A nanometer being 1,000th of a micron being 1,000th of a millimeter, we are getting very close to the point where we're getting down to individual atoms on the devices that we're able to manufacture. So we can ask ourselves, what is the world made of? What is the limit to how small we can make a computer chip? Can we go down much smaller than tens of nanometers? We can ask ourselves what the world is made of, and we can ask ourselves, well, how do we know what the world is made of? What clues do we have that tell us about the nature of matter? Now, philosophers have been talking about this for many a long century, many a long millennium. Aristotle, for instance, said, well, everything is just made of 4 elements, earth, air, fire, and water. That makes the periodic table really simple, but unfortunately it doesn't explain all the complexity that we see around us. And it wasn't until what you might call real scientists, with all due respect to Aristotle, came along, people like Galileo, who said, we shouldn't be asking about how things ought to work, we should be doing quantitative experiments. If we want to know how the world works, we should do experiments and find out how the world works. Not qualitative arguments as to how we think it should work, but quantitative experiments telling us how it actually works. In other words, we shouldn't ask, what should happen if, which is what the ancient Greeks tended to do. When you drop an object, it ought to fall to the ground. We should actually do the experiments and find out what actually happens. And then along came Newton in the 1600s doing a lot of different experiments, and who formulated what we now call either Newtonian mechanics or classical mechanics. He gave us the ideas of the laws of motion, how things behave, the universal law of gravity, and he also did experiments on the nature of light. So he didn't necessarily tell us what the world was made of, but he laid the foundation of how we go about thinking about what the world is made of. We get this idea of a clockwork universe. As far as Newton was concerned, regardless of how everything came to be in the first place, the universe is thought to be clockwork. Wind it up and it just goes based on the laws of physics as we understand them. So the planets go around the sun, the moon goes around the earth. If you drop an apple, it falls to the ground, etc. Everything is clockwork. And that seemed to be a good way of thinking about how the universe works until relatively recently. What clues do we have about the nature of how matter is put together? Well, if we look at materials such as, for instance, ice, if we look at snowflakes, we find a certain pattern. We see the fact that they all seem to be six-fold symmetric. So either you say it's magic, or you say there's a reason that all snowflakes appear to be six-fold symmetric. There must be something about the structure of ice that makes snowflakes want to form this particular pattern with this particular symmetry. So there's an intellectual argument, if you like, which leads us to a conclusion. If objects are six-fold symmetric, the underlying building blocks must be six-fold symmetric in order to lead to that particular result. And if we look at different materials, something other than ice, this happens to be an element called bismuth. When bismuth goes from a liquid to a solid, it forms this particular type of crystal structure. We may not understand what's going on, but there are definite angles there which would imply if this stuff is made of building blocks, these building blocks want to fit together in 90-degree angles. Unlike the six-fold symmetry of snowflakes, whatever the building blocks are here, they want to fit together in either squares or rectangles with 90-degree angles. So again, we get a hint of the underlying structure. We see that in a number of different minerals where the minerals themselves want to form particular crystalline structures which look like small cubes, or more recently we can develop alloys of materials which want to form crystals with the more bizarre shapes, for instance the dodecahedron. Why on earth would material want to get together and form not necessarily six-fold symmetric snowflakes and not necessarily 90-degree angles of squares and rectangles? What on earth would make atoms want to get together and form a structure that results in a dodecahedron? So that hasn't been machined, that's how it wants to form. And, the macroscopic shape that we can see easily because it's on a scale of millimeters or centimeters, the macroscopic shapes that we see there basically give us clues to the underlying structure. Now, I'm not going to turn this into a history lesson, but just to give an idea of what happened. We've got Democritus on the left-hand side there, way before 1600, of course, way off on the left-hand side, and a few other key players who, during the 1600s and 1700s and 1800s, started to formulate the ideas of what these building blocks must be. Some of it came from alchemy and ultimately chemistry as to what the building blocks are that result in the world that we live in. I'm not sure how good your history is, whether you already recognize any of these faces. Let's just go through a few of them. We've got Boyle, you probably recognize Newton, then we've got Lavoisier, then we've got Dalton, and then here we've got Avogadro, and on the top right we've got Maxwell, and in the bottom right we've got Boltzmann. I'm not going to go through each of their contributions, but all of these scientists made a contribution towards understanding what must the building blocks be and how do they fit together in order to give us the world around us. Things seem to be going quite well, but in 1800, during the 1800s, there was a little bit of a revolution going on in the background where we were trying to understand the nature of matter and the nature of light as well. Newton started this in the 1600s, but in the early 1800s, Young did experiments on light that showed that light is a wave, an interference pattern. You can only get interference from a wave-type structure. When waves add together and give you troughs and crests that add together, you get higher troughs and lower crests, you get interference. And in certain cases, waves add together and destructively interfere with each other. So if you see this phenomena of interference, you know you're dealing with a wave. So Young established the nature of light in the early 1800s was quite definitely a wave. And later in the 1800s, J.J. Thomson was looking at these newfangled particles that had been found called electrons and established, well, yes, they are particles. They're not waves, they're particles. So in the 1800s, it was established that light is a wave and an electron and other things that we think of now as particles are indeed particles. So things were looking reasonably sound up to the turn of the century, 1900 or so, but the next few decades were, well, tumultuous to say the least. And again, here are the key players. We haven't got time to talk about the contribution of each of these key players, but once again, perhaps some of these you recognize, maybe some of them you don't. So we're talking about Becquerel, who discovered radioactivity, Planck, and then Rutherford, who discovered the atomic nucleus, Einstein, whose contribution we all know about, Bohr, who gave us information about the structure of the atom, de Broglie, and then on the right-hand side, Heisenberg and Schrödinger, who ultimately became the architects of quantum mechanics. So a lot of things were going on during these only 3 decades or so. A huge amount of discoveries were made, not only the initial discovery of radioactivity back then in the late 1800s, but various ideas have now been overturned, because having established last century that light is a wave, along comes Planck and says, no, light is a particle, or at least can be considered as a particle. And a little later on, de Broglie, despite last century having established that electrons are particles, along comes de Broglie and say, well, no, electrons are waves, or at least can be considered as a wave. About this time, it was established that atoms exist as a positively charged nucleus and negatively charged electrons, thanks to the work of Rutherford and others. And it was also established that probability plays a key role in understanding the nature of how atoms are put together. So you can see an enormous amount of confusion. Well, what is light then? Is it a wave or is it a particle? What is an electron? Is it a particle or is it a wave? Why are we getting apparently different scientists saying different things? So a huge amount of confusion, some of which was resolved by Heisenberg and Schrödinger, putting together the structure of what we now call quantum mechanics, or quantum theory, if you prefer. A relatively unified way of looking at all of the results that have been acquired in past decades and ultimately past centuries. So a very confusing time, and part of the nature of the weird world that I'm talking about is what quantum mechanics tells us about the nature of how atoms are put together and how atoms make molecules and ultimately us. So this is the picture we tend to have in our heads. Whenever you say atom, you tend to think of, well, an atom is a positively charged nucleus made up of something or another, and negatively charged electrons buzzing around it like bees in a beehive. So that's a very nice sort of graphic. It's not right, it's not the way atoms actually exist, but it's a perfectly good way of visualizing it for the benefit of simply having something to go into your head. This is a problem that I'm about to come to, is that part of the problem with trying to figure out what atoms are doing is how do you visualize what an atom actually is? Because on the scale of the very, very small, a lot of what we think we understand about the nature of the world around us, a lot of that has to be sort of put to one side and parked whilst we think about the nature of atoms. One thing in particular that this diagram doesn't tell us is that all the electrons are different in an atom. Here it looks like all the electrons are doing the same thing. They're going around the nucleus apparently in little orbits at the same speed, at the same distance. But actually, it doesn't tell us that when you have an atom, we know by making measurements that all of the electrons, most of the electrons, have different energies in any given atom. And therefore, this particular model isn't very good. A slightly better model is to think of it in terms of these shells. Three-dimensional shells, but if we imagine taking a shell and just collapsing it down to a two-dimensional picture, instead of having all the electrons at the same distance doing the same thing, we now have electrons at different distance from the nucleus, which would represent the idea that they are actually at different energies as they effectively orbit the nucleus. But even this concept of orbiting and thinking of it like a solar system is misleading. So the idea of shells, or at least orbits or shells, that's one step better than the previous picture. It's still not right, but at least it gives us the idea that different electrons have different energies, and that gives rise to the different properties of different atoms, which is why all the atoms that we see in the periodic table all have slightly different characteristics and different properties. We have something of order 92 stable elements, and I've lost count of how many unstable elements have now been made in the laboratory, but we have of order 100 or so elements, each of which has different properties, from the hydrogen, helium, lithium, beryllium at the light end towards the very heavy uranium, plutonium, etc. at the other end of the periodic table. We now have a relatively good understanding of why they are arranged in this particular way, why they are arranged in a periodic table, because the properties of these elements appears to be periodic in the sense that when you look at particular elements, they seem to be cousins to each other and have very similar chemical and sometimes magnetic and sometimes physical properties. We understand that on the basis of what those electrons are doing. And so studies over the last 1 or 2 centuries of what those electrons are up to have allowed us to make sense of putting them into a table like this and make sense of their properties. But we can still ask the question, well, is it right to think about the electrons buzzing around the nucleus like the planets go around the sun? Is an atom just a mini solar system? Well, no, it isn't. We can sometimes think of it that way for the convenience of simply having a picture in our heads, but that's not actually what is going on. One way to think about it is to say, well, electrons don't simply go round the nucleus in a nice circular or even elliptical orbit, as planets do go around the sun. We have to think of it instead in terms of, if I wanted to measure where the electron is, what's the likelihood of finding an electron here, or finding an electron there, or finding an electron anywhere else? Each of these clouds, you can imagine there's a center to each of these. That's where the nucleus would be, not shown in these particular diagrams. And these fuzzy looking clouds are effectively telling us bright means we're likely to find an electron there, dark means we're not likely to find an electron there. So an electron can exist in various states in an atom where we can never say it is here, we can never say it's moving at this speed, we can never say it's actually doing this orbit. All we can do is to say, for this atom, for this electron, the probability of finding it at any particular place is given by a fuzzy-looking cloud like this particular diagram. So we have to throw away the idea of determinism and a clockwork universe and say we absolutely know where things are. We have to put that to one side. The only real way to describe things like atoms and molecules is to say we know something about the probability of the system existing in a particular state. So how are we going to actually deal with atoms? How are we going to understand the properties of atoms? How are we going to teach atomic physics to our students? Well, one option is to use words in much the same way that I have been so far. We can talk about particles and waves, and we can talk about electrons, not strictly speaking in orbits, but we can talk about the fact that an electron spins and an electron orbits around the nucleus, or at least has a certain amount of so-called spin angular momentum or orbital angular momentum. But the problem is those words were designed in English long before quantum mechanics came along. So those words have connotation. When we talk about the spin of an electron, we imagine the spin of the Earth, and we think about the Earth spinning on its axis. And we use the same word to describe a particular property of particles, but it doesn't mean the same thing, even though we very loosely talk about it as if it did. And when we talk about an orbit, we don't mean an orbit in the sense that the Earth orbits the Sun, but we still use the same word or a similar word to describe how electrons behave. And that is a problem. If you're using words which have got more than one meaning, one in common or garden English and one in the specific meaning of quantum mechanics, if you're using the same words, you're going to get confused. You could say, well, we'll get rid of that confusion by just dealing with pictures. But we know the pictures are wrong. The idea of a picture in which electrons are buzzing around a nucleus, we know that's incorrect. And even if we say, well, we could have a picture in which we've got clouds, well, we still know that's wrong in the sense of that's not complete. The only real way of dealing with atoms and molecules and the world of the very, very small, unfortunately, is maths. Sorry about that, that's it. Words are not designed to talk about the nature of atoms. Words are part of an English language that was developed or has been developing for millennia and is not the right set It's not the right toolbox to use when we're dealing with atoms. Pictures, we like pictures because, well, we're humans and therefore we like to be able to see. We like to be able to visualize what's going on. But we have problems when we try and visualize what's actually happening. So the only solution is maths. And maths, unfortunately, even though we teach the maths by, of course, teaching the maths by using words, and we occasionally use pictures to try and explain the maths we're trying to teach, the maths is, well, horrible, basically. It's not the sort of kindergarten maths that you can get away with. Simply knowing your times table doesn't help when it comes to quantum theory. You need mathematics, you need specialist mathematics tools that allow you to cope with the quantum mechanics we're dealing with. So whenever you say you can't understand quantum theory without maths, the usual reaction is, oh dear. Yep. And part of the problem is that when we're trying to teach students at university about quantum theory and about the nature of atoms and the nature of molecules, there's a whole load of difficult concepts to get across, most of which are contrary to common sense. So you've got that hurdle to overcome, and to give them the tools they need to actually deal with the problems, you need to give them a whole set of new maths that they're not familiar with. So there's a double whammy. The concepts are counterintuitive and the maths is not straightforward. And that's part of the problem with teaching any student, regardless of whether they're a youngster or an oldster, teaching them about the nature of quantum theory. Heisenberg, one of the architects of quantum mechanics, said, "We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language." This was recognized 100 years ago, back in the 1930s. We want to talk about atoms, but the English language is not up to the job. You could argue that we ought to throw away the words. Rather than use existing words to describe an atom, instead of saying electrons orbit and spin in the atom, should we instead say that the slithy tote did Gaia and Gimbal in the wave? Because those two sentences in red carry exactly the same amount of information. If you don't say what you mean by an electron, if you don't say what you mean by an orbit, if you don't say what you mean by spin, if you just assume that those words have some meaning, you'll get as much response as basically saying that. So perhaps we should, in the first place, have not used all of these words twice. If it isn't actually spinning, we shouldn't use the word spin to describe that property of the electron. But it's a bit late now, because we've been using that word for the last 100 years, and it's almost impossible to backtrack. And the lack of clarity regarding the lack of common sense when you start applying the maths and getting results really doesn't help. Here's Bohr, again, one of the architects of the early quantum mechanics. Everything that we call real, because I believe that table is real, as to the best of my knowledge, and yet it's made of atoms which seem to have this ghostly property that they are not made of something solid, not made of anything that we can say, yep, that definitely is there and that is moving in the following way. Everything we call real is made of things that cannot be regarded as real. And you have to stop and think, well, how are you going to deal with the world then, if that is actually the case? Atomic physics has shown us that atoms have no meaning. Again, that's a hell of a statement for any physicist to make, but can only be understood in experimental measurement. This is one of the key concepts in quantum mechanics, which takes a little bit of getting used to, is that quantum theory tells us how the world works, but in effect it tells us, if I were to make a measurement of something, what will I get, or what's the probability of getting a particular result? It doesn't necessarily tell us this is the way it is. It tells us, if I were to make a measurement, what will I get? And that's the power of quantum theory. Philosophers will argue about, yes, but what does it mean? Is that the way it is, or is that just a way of getting to an end result? Quantum theory tells us a way of answering the question, if I make a measurement, what will I find? I don't like it, and I'm sorry I ever had anything to do with it. This is one of the architects of quantum mechanics. This is the person, Schrödinger, who we all dearly love for his equations that allow us to get a handle on the way the quantum world works. And yet he was never happy with the whole idea and basically wanted out. The main problem is that quantum mechanics and common sense do not agree with each other. And here's just 3 examples of in what way common sense and quantum mechanics disagree. Atoms are unpredictable. They are not clockwork things that we can wind up and watch go. You can only know about the probability of certain things happening. For instance, we can calculate to extreme precision the probability of an atom having a particular position in space, or having a particular speed, or having a particular energy. We can calculate what its properties are likely to be. But that doesn't mean that we know absolutely where it is and what it's doing. We can simply calculate how it is going to behave. And although we tend to think of atoms as small, we tend to think of them as minute building blocks of everything, strictly speaking, atoms do not have a size as such. Because if we ask ourselves, if I've got an atomic nucleus here, where am I likely to find the electron? Well, the answer is yes, you're most likely to find that electron close to the nucleus of the atom. But you could find it a millimeter away, or a meter away, or a light year away. It's just very, very unlikely. But the answer isn't 0. The probability of finding an electron a long way from its host atom is not 0. It's just a very, very, very small number. So you could argue that atoms do not actually have a finite size. It's simply that there's a probability that most of the electrons are found close to the nucleus. The other thing that goes against common sense is that atoms can be in 2 states at the same time. We're used to the idea that if we toss a coin and it comes down onto the back of your hand, the answer is either heads or tails. It's one or the other. But in the quantum world, we can be in 2 states at the same time. That applies for a particle, it applies for an atom, it applies for a molecule, and we're not too sure whether it applies for anything bigger. But the bottom line is, an electron, if we think of an electron spinning, again, the wrong word to use, but if we think of an electron spinning, it can spin clockwise and anti-clockwise at the same time. Now, the Earth can't do that. The Earth spins one way or the other. You either look at it from above the North Pole or from below the South Pole, and you get it's either spinning clockwise or anti-clockwise. But when we look at the subatomic world, it looks like things can exist in 2 states at the same time. And that goes completely against common sense, because that's not what we see in the world around us. But just because that's not what we see doesn't mean it isn't actually happening in the quantum world. Common sense is the collection of prejudices acquired by age 18. In other words, common sense is just common sense. It's just the commonality of what we sense in the world around us. Whenever quantum mechanics has come head to head with common sense, and quantum mechanics has told us something that goes completely against common sense, every test we've done so far has shown that quantum mechanics is right and common sense is wrong. So even though you've lived with common sense for many decades, that doesn't mean it's right. It's been fine for getting you through your day-to-day life. It's been fine for making sure that you go through your childhood, you go through your adult life, you pay your taxes, etc. But in terms of understanding the quantum world, common sense, unfortunately, doesn't work. When we toss a coin, we think of it coming down heads or tails. But Einstein was never happy with this idea that we can only describe the properties of atoms or anything small by talking about the probability, as opposed to it is this or it isn't that. The idea that God plays dice, in other words, everything is dictated by probability and you cannot know anything, you can only talk about the probability of something happening, this was something that Einstein was never happy with. God does not play dice, he says. God is subtle, but he is not malicious. The idea being that anything that's based on probability is malicious rather than nice and easy to work with. Einstein said God does not play dice. He argued with Bohr, who said, stop telling God what to do. If this is the way the universe is, and all measurements would imply that this is the way the universe is, then it's been set up that way for whatever reason, but it looks like, yes, God does play dice. Let's look at 3 particular aspects of quantum mechanics that illustrates what I've been talking about. The fact that order matters, I'll say what that means in just a moment. The idea of Schrödinger's cat, a thought experiment. And let's finish by actually using quantum mechanics to actually see the quantum world. So firstly, order matters. We're used to the idea when we do very simple maths, we're used to the idea that A times B is the same as B times A. Because we're all used to, since we were given our times tables, that 2 times 3 is the same as 3 times 2. Doesn't really matter which way round you put them. But in quantum mechanics, the order does matter. A times B is not the same as B times A, where A and B represent, I want to know about 2 properties of this particular system sitting in front of me. I want to know, with this atom floating around in front of me, I want to know where it is and I want to know how fast it's moving. Those are the 2 things I want to actually measure. Here they're just labelled A and B. But the order in which you make measurements matters in quantum mechanics, whereas in standard algebra it doesn't. Let's just take a thought experiment and imagine what if the rules of quantum mechanics applied in the macroscopic world that we see around us, so that common sense was no longer a problem. Let's imagine we had a menagerie, a wildlife park if you like, with only 4 animals in it. There were only 4 animals. You can see a lion, a vulture, a waterbuck and an ostrich. The top pair, the top 2 animals are both carnivores. The bottom 2 are both vegetarian. An alternative way of thinking about it, there's the 2 carnivores, the lion and the vulture, and there's the 2 vegetarians, the waterbuck and the ostrich. But we could also think of it as 2 pairs the other way. The 2 animals on the left have got 4 legs, the lion and the waterbuck, and the 2 on the right have got wings. So there's the 2 4-legged animals, there's the 2 winged animals. Yes, I know ostriches can't fly, but they still have wings, okay? Right. So there's wings on the right, 4 legs on the left. And here's the bizarre result of quantum mechanics. What if I wanted to separate these animals out? What if I wanted to pick 2 out of the 4 animals to start with? For instance, what if I were to say I want to pick the veggie animals? So if I wanted to basically take the veggie animals and corral them off, separate them out from the carnivores, I would take the veggie animals to one side, and then I would make another separation, if you like. I now want to filter them out. From these vegetarians, I want to pick again. So from the 2 vegetarians I've just selected, I'm going to pick the 4-legged animals. So having picked out the waterbuck and the ostrich, I'm now going to pick the 4-legged animals, so I expect to be left with the waterbuck. But quantum mechanics says no. If you take the vegetarians and then from them select the 4-legged animals, you're going to be left with a waterbuck and the lion. Even though you've selected the vegetarians, the lion is back. That doesn't make any sense in common sense. Having already selected the vegetarians, the lion shouldn't be there. But in quantum mechanics, if you select one and then select the other, the second selection, as it were, overrides the first. Even though you've already selected and corralled them off, somehow or another, the lions pop up again. And if you were to change the order in which you were to make that selection, what if we first pick the 4-legged animals? So we're going to pick the lion and the waterbuck. And from those, we're now going to say, let's take them to one side, and now let's separate them out into the vegetarians. You would expect to get the waterbuck, but having selected the 4-legged animals and then the vegetarians, you find the ostrich is back. The order in which you do it makes a difference. That's what the world would look like if the macroscopic world obeyed the same rules as the quantum world. It disobeys common sense, and it needs a separate, if you like, set of maths and a separate way of thinking to understand how that affects the way atoms behave, the way molecules behave. In the second example, Schrödinger's cat, the idea is we kill a cat. Now, I know that's rather panicky for most cats, but no, it's a thought experiment in which we say, Schrödinger said, let's think about this. What if different states of an atom or states of a particle, it doesn't matter. Let's imagine this atom can be in 2 states at the same time. Most people say, well, that's way beyond our experience because we can't actually see individual atoms, but let's imagine that is possible for an atom to exist in 2 states at one time. Schrödinger then set up this thought experiment and said, what if that state of the atom then led to the state of a cat? In other words, let's imagine we have an atom. Let's just assume that this atom is radioactive and might decay into something else. All that matters is it might decay, it might not. Let's assume that over this particular experiment, there's a 50-50 chance of this atom decaying or not decaying. And according to our understanding of quantum theory, if we put it in a box and do not look inside the box, then that atom is in the state of being decayed and not decayed at the same time. It's in two states at the same time. Inside this box, the state of the atom goes into a Geiger counter, which picks up whether it's decayed or not by spitting out some radioactive material, spitting out some particle from the atomic nucleus. And the Geiger counter then sends a command to this robot with a hammer, which then smashes a vial of poison, which either kills the cat or not. The box is closed, so we do not know whether the atom has decayed or the atom has not decayed. We do not know whether the cat is alive or dead. But the fundamental result of Schrödinger's cat is to say, if we don't open the box, it's not simply good enough to say, this has happened, the atom is either in this state or that state, it's either heads or tails, and therefore the cat is either dead or the cat is alive, but we don't know which yet until we open the box. No, according to quantum theory, it can exist in both states at the same time. So if the atom is in both states at the same time, the cat must be in both states at the same time. Before we open the box, the cat must be dead and alive. This is the paradox of Schrödinger's cat. Even if we accept it at the quantum level, Schrödinger's cat experiment says, well, if you have consequences from the quantum level up to the macroscopic level, that gives you a paradox. It means that it is possible to have a cat that's alive and dead at the same time. When we open the box, then the cat becomes dead or becomes alive depending on which way the atom actually went. Did it go for A or B? Does it go heads or tails? But whilst the box is closed, the cat is in both states. That completely disagrees with common sense, but we have to come to terms with that, because whenever quantum mechanics disagrees with common sense, it looks like common sense always loses out. So philosophers have been wrestling with this idea for the last 100 years or so. But why do we put so much faith in quantum mechanics? How do we know it's right? Well, we don't. You can never prove a theory correct. But quantum theory has been with us for about 100 years now, and it has been tested over and over and over and over again for essentially every day of this last 100 years or so. And so far, nothing has proved quantum mechanics wrong. Quantum mechanics has produced lots of different ideas, lots of different predictions, many of which go completely against what we understand from classical mechanics. Quantum mechanics tells us this should behave like that, and gives us results that are impossible to predict with good old-fashioned Newtonian mechanics. The physics as understood by Newton are not capable of explaining some things about the quantum world, about the world around us. And yet quantum mechanics is. So not only have we never proved it wrong, it is time and again given us results that classical mechanics from 400 years ago has been unable to deal with. And using quantum theory, we can actually build a microscope to actually see atoms. This is the microscope. It's called a scanning tunneling microscope. Tunneling is a particular property, a quantum property. If we were to bring a sharp tip, each of these little balls here represents an atom. So we're looking at a tip coming down onto a surface. We're just looking at the last few atoms of the tip coming into contact with a few atoms on the surface. So I'm not interested in all the trillions of atoms below here or all of the trillions of atoms above there. If this was an electric circuit with a voltage and an ammeter measuring how much current flows, there would be no current flowing until this touches, because it's a broken circuit, therefore no current flows. But quantum mechanics says, as long as D isn't too large, it is possible for an electron to exist in this no man's land, even though, according to our understanding from classical mechanics, from Newtonian physics, it should not be possible for an electron to exist in this space in between one and the other. But according to quantum theory, there is a finite probability that the electron will spontaneously go from one part to the other and a current will flow. And what we actually find is that the current does flow, and indeed the current flows in such a way that it's dependent on that distance in a way that is exactly predicted by quantum theory. Classical mechanics says the current should be zero. Quantum theory says the current will depend on d in the following way, and that is exactly what we find. So in terms of building a microscope, what we do is bring a tip fairly close to a surface, and as we move the tip across, either the distance changes or we measure how much current flows and we alter the height of the tip to keep it a given distance above the surface of the metal, the semiconductor, the material, whatever it is that we are trying to study. So moving a sharp tip across a sample gives us an extremely sensitive measure of what's going on, and we can resolve individual atoms on a surface by moving a very sharp tip over a surface. A bit like if I move my finger over my knuckles, the distance keeps changing as I go across my knuckles, and that distance gives us a changing current which we can measure. And these scanning tunneling microscopes invented in the 1980s have been used extensively since then. Ignore the handsome physicist in front of the microscope. That's the microscope in the background. The microscope is kept inside a vacuum vessel to keep everything nice and clean. The last thing we want is oxygen and nitrogen and other things getting in the way of our measurement of particular atoms or molecules on the surface. So we keep it in a vacuum vessel at an atmospheric pressure of about 10 to the minus 13 atmospheres or so. And we end up with pictures that look a little bit like this. This is now a very old picture, but I like it. It was taken by a colleague of mine back in the days when we had a collaboration between the University of Liverpool and the University of Manchester. Notice the scale here. This is 2 nanometers. And we're seeing a 3-dimensional projection of what this surface looks like, and each of these mountain peaks here represents atoms on the surface. This is the surface of rust. This is the surface of iron oxide. It's actually a combination of Fe2O3 and Fe3O4. And you can see that there are little islands where the peaks here are quite high, and then there are some smooth regions and other islands which, again, have a whole load of peaks. You might also notice the islands themselves are lined up a little bit like the peaks inside the islands. The islands themselves are lined up in a regular pattern. So we are capable of seeing individual atoms of iron and oxygen on the surface, and therefore we're capable of looking at how atoms interact with each other. If we wanted to put molecules on the surface and see how they interact, again, microscopes like this with atomic level resolution can see individual atoms and individual molecules and start to look at the interactions that we can calculate from quantum theory to establish whether quantum theory is giving answers that make sense. We see patterns large and small. For instance, this is an alloy. Again, the scale here is 10 nanometers or so. And at first sight, perhaps you don't see much, except every once in a while your eye gets caught by a 10-leafed sunflower. Or if we look in detail at certain structures, let me just highlight it, there is a pentagon. There seems to be a pentagonal arrangement of atoms in this particular structure. And when we realize that the atoms are arranged in pentagons, it then makes a whole lot more sense to realize that's why this particular alloy wants to form a dodecahedral crystal when it goes from a liquid to a solid. Again, we didn't realize it until we started looking at the atomic level, but yes, whenever we see macroscopic symmetry, there's usually a microscopic reason. The microscopic arrangement of atoms tell us why the world is put together on a scale that we can see each of these squares being a millimeter here. Not only that, we can start to measure the distances between atoms to try and understand how these atoms are interacting with each other. We look at the distances between atoms, and we find that when we take certain distances, a particular ratio of distances keeps cropping up. If we look at the ratio of the distance between those atoms and the distance between that atoms, we get a particular ratio. And it's the same ratio down here and the same ratio up there. And it's the same ratio for these atoms and it is for those atoms. That ratio, it turns out, is 1.618. The same ratio that you get if you look at, for instance, pineapples. If you look at pineapples and count the scales one way through a spiral, and count them the other way through the other spiral, the ratio of how many scales you have is approximately that same number. The same is also true if you look at sunflower heads. Again, two sets of spirals. You can count the seed heads going one way in a spiral. You can count the seed heads going in the other spiral. Those two are not symmetrical. One divided by the other is 1.6 and a bit. So things that we see on the quantum scale sometimes are reflected in things we see on the macroscopic scale. Is this a coincidence? Is there something interesting underlying about this particular number, 1.6? I'm not suggesting for a moment that the interaction of atoms on this scale is necessarily influencing the arrangement of seeds in a sunflower head, but something is going on that gives us a particular symmetry between what's going on in the atomic world and what's going on in the macroscopic world. Here's a false color image of a very interesting surface, again, one that was generated many decades ago. It's interesting for a number of reasons, not least because we have a whole load of apparently mountains in this big corral here, indicating that these atoms, or whatever they are, appear to be very specific particles that are lined up, and there are, I don't know, 50 or so of them arranged in a large circle. This has been done by the person operating this microscope. They have placed a whole load of atoms in a big circle to make a corral. So these atoms are behaving like particles. They've been picked up and moved and put down somewhere else on the surface. But look what's going on inside the corral. Inside the corral, there appear to be a whole load of ripples. It's just like there's a pond in there and you've thrown a stone into the middle and it's produced a whole load of ripples. In other words, what we're looking at is a surface in which some of the atoms appear to be behaving like particles. They've been moved into a large circle and they've stayed there. But inside, whatever's going on there, the electrons in this particular system are behaving like waves. So in one image, we have the quantum world telling us that sometimes things behave like particles and sometimes things behave like waves. And that's part of the confusion and part of the duality that we simply have to live with. We would like it to be nice and simple. We would like light to be a wave and an electron to be a particle. But sorry, they're not like that. They both have wave and particle behavior, wave and particle characteristics, if you like. And a picture like that reminds us that even in the same image, we can see two things happening at the same time. If quantum mechanics hasn't profoundly shocked you, you haven't understood it. This is a very popular quote whenever you teach quantum mechanics at university level. If you think you've understood it, you haven't. If you're shocked by it, then maybe you have understood what was going on. But if you're not shocked, then if you're simply taking it for granted, you're not really thinking about the consequences. Whenever quantum mechanics disagrees with common sense, you get a little bit of a shock, asking yourself, is that right? Can it really be like that? One of my favorite quotes from Einstein is that, quote, the most incomprehensible thing about the world is that it is comprehensible. Given enough time, given enough thought, you can actually figure things out. Now, we've only had 100 years to think about this in the sense that we didn't know the quantum world existed before about 100 years ago. And it's taking a little bit of time to rewire our brains because our brains are wired up in a particular way. Our whole brain and eyesight system is based on the idea that was that flash of light a lion that's about to eat me, or where's my next meal coming from? Our brains are not wired in a way that allows you to understand quantum mechanics from birth. It has to be something you have to think about. But the amazing thing is, although the universe owes us nothing, it is actually possible, given enough people with enough ideas and enough experiments and enough thought, it is possible to build a structure, to build a theory in which we can start to make sense of the quantum world. Yeah. So it does take a bit of thinking about. And so if you're bamboozled, don't worry. Just about every student I've ever taught has been bamboozled at some point or another in their quantum mechanics lectures, because it is not something that your gut can tell you is right or wrong. For most of their schooling, students are taught, when you get an answer, think about whether it makes sense or not. With quantum mechanics, you can't use your gut to tell you whether or not that answer sounds right or not, because even though it sounds wrong, it might still be correct. So yes, we still have an awful lot of thinking to do. Maybe in another 1,000 years, our brains will slowly rewire themselves so we have it easier, maybe a little more natural, the idea that we can understand the quantum world. Let me finish with this image. It's an image where the scale is 850 picometers across. A picometer is 1/1000th of a nanometer, which is 1/1000th of a micron, which is 1/1000th of a millimeter, which is 1/1000th of a meter. So this image is less than 1 nanometer on a side. And we're looking at individual atoms in a scanning tunneling microscope here. And just to give you a sort of sense of scale, if that is the structure of matter, on this scale, a grain of sand would be about the size of the moon. That gives you an idea of the magnification of a microscope like this. And whenever I see a scanning tunneling image of individual atoms, I always think of the William Blake poem, which starts with, "To see a world in a grain of sand." Thank you all very much for listening.